Okay, so here are the notes for section 10.3, arcs and chords. So this section, yeah, it's basically dealing with how arcs and chords are related. So there are a few big theorems in here, and then kind of some application stuff to work out. So we'll just jump into it. We've already used relationships between arcs and angles to find measures before. So now we're going to talk about what about arcs and chords, and then arcs, chords, and diameters. So theorem 10.2 is the first one to start off with, and theorem 10.2 says in the same circle or in congruent circles, excuse me, two minor arcs are congruent if and only if their corresponding chords are congruent. So here's kind of an example of that right now, and again, hopefully that's kind of showing up for you. But you have arc CD, which is the arc in red, arc EF, which is the arc in blue, and then here's chord CD, and here's chord EF. And right now, the two chords are different sizes, as are the arcs. But if I move this so that CD is as big as EF, so it's like 5.33, there you go. Both the arcs are the same. So that's basically all it's saying is, hey, if two chords are the same size, they'll cut off arcs that are the same size. Or vice versa. If two arcs are the same size, they'll cut off chords that are the same size. So let's look at an example that involves that. So here's the question for you here. In this figure, solve for x. Okay. And then, yeah, I'll come back. Okay, so to actually solve for x in this one, oops, wrong button. I always do that. I have two circles, A and B, and this is kind of using that second form of the theorem. If we go back here, normally it's within the same circle, but this one they said in the same or congruent circles. Okay, so here we have two circles that are congruent, they're not the same circle. But the two arcs, YZ, the minor arcs, and WX are congruent, so the question is, what's the measure of WX? Well, if the two arcs are congruent, that means the two chords are congruent. And if the two chords are congruent, that means 5x plus 6 has to equal 7x minus 2. So subtract 5x, add 2, 8 equals 2x, divide by 2. 4 is equal to x. So plug 4 back in, 7 times 4 is 28, 28 minus 2 is 26. Or over here, 5 times 4 is 20, 20 plus 6 is 26 as well. Okay, the next theorem. This actually is a really, really good theorem. We should have a day at the end of the chapter. It just depends upon snow days and whatnot and spring break. But we'll have a day where we'll actually do this ourselves. Well, I'll give you a circle. We'll do constructions and we'll find the center of a circle. And that's what these two theorems basically do. The first one is really the flip to the second one, the converse to the second one. So if we have a diameter or a radius of a circle and it's perpendicular to a chord, so diameter and radius are automatically on the center of the circle. If you're perpendicular to that chord, you bisect not only the chord, so xz and zy, but you're also going to bisect the arc of xb and by. Okay. Now, the other one here says if you are the perpendicular bisector of a chord, you are the diameter. So basically, if you know that you cut through a chord, cut it in half, and you're perpendicular to it, you're also going to be on the diameter. And that's really where the power for this one comes into play. So here's the theorem for that. So right now what I've got is I've got segment CD. What I'm going to do is with the computer, I'm going to find the midpoint of this segment. And then what I'm going to do is I'm going to construct a line that is perpendicular to this segment that goes through point E. And it's going to go through the center. And there it goes. And no matter what I do with that now, no matter how I move it and draw it around, this always goes through the center. And I know it already bisects it because I made it bisect DC, so DE is equal to EC. And then the arc, you can kind of see too that, yeah, it looks like it cuts that arc in half. Okay. So the theorem is if you're perpendicular to a chord and you go through the center, you're going to cut the chord and the arc it's made by in half. Flip side, though, is this. If you have a chord and you can construct a perpendicular bisector of it, you're going to go through the center. Okay. So here, let's look at a problem. So they told us that the measure in circle Z measure of angle WUX is 160 degrees, find the measure of arc UX. Okay. So this one might seem weird until you see someone do it, but it's not terribly involved as a problem goes. Okay. So here's the deal. Even though this isn't a major arc, because 160 degrees is less than 180, they did the three-letter name because there's all this different stuff going on, and we're actually going to find the measure of just UX. So here's what we know. We know this arc here in blue that I'm tracing is 160 degrees. Okay. Now the question is, how big is this guy right here in red, UX? Well, what we have to realize is that ZU is a radius, and it's perpendicular to chord WX, meaning this is congruent to this. That's also 7. But that also means then that our two arcs are congruent. So if 160 is the whole arc, each of those has to be half of it, 80 degrees. Okay. All right, last theorem then, theorem 10.5. In the same circle or in congruent circles, okay, just like before, two chords are congruent if and only if they're equidistant from the center. Okay, so the only way that FG can be congruent to JH is if it's the same distance from the center. And I've got that on a slide here for you too, and again, hopefully you can see it. Right now, AG is closer to the center than AH is. Okay, so CD is closer to the center than EF is, and you can see CD is bigger than EF. But if I move point F so that AH and AG are the same length. Whoops, I just skipped over that, didn't I? 158. Oh, come on. There we go. Whew. So AG and AH are the same length. That makes the two chords the exact same length. And it works the other way around. If I go, no, let's move this to this so that I want to make CD the same length as EF. So I'll make CD smaller, or it's 3.39. Hey, guess what? 3.39 to 3.39, 2.24 to 2.25. That's just round off error the computer's doing. So if you are equidistant from the center, the two chords are congruent. If they're in the same circle or if they're congruent circles. So for this problem here, we are going to figure out the length of PQ. Okay, so if we look at the drawing of it then, EF is equal to GH and is equal to 24. So what I'm being told then is this chord, EF, is congruent to this chord, meaning that this segment here of QP has to be congruent to RP. Okay. So in order for that to happen then, to find the length, I'm going to set 4x minus 3 equal to 2x plus 3. So add 3, subtract 2x, subtract 2x, 2x equals 6, divide by 2, x is 3. If you say, yeah, 3, you're wrong. The last part of this is find the length of PQ, not find the value of x. So you have to take x and plug it back in. So 9. So there's length of PQ. It's equal to 9. Okay. So that's it for section 10.3. Yeah, I got under 10 minutes. Fantastic.